It's another math day here with teacher Jenny. Join me for another topic. This time we're going to talk about continuity of a function at an interval of a piecewise function. Determine if the function is continuous at the given open interval. F of x equal to 1 if your x is less than or equal to 2. F of x equal to x squared minus 3 if x is greater than 2. The interval is open at 2, 4. Now, once we have an open interval with a symbol like this, our open interval has really a symbol like this. This would simply mean that if you try to draw a number line, this, let's say this is 2, this is 3, this is 4. Our 2 here is open, our 4 is open, meaning it is not included or part of the domain. What is part of the domain are the ones in between them, meaning we have 3 as part of the domain, we have 2.5, 3.5, 3.9, 2.1, and so on, as long as you do not include 2 and 4 and outside those boundaries. Now, we are going to check first whether in this particular domain we do have a problem with obtaining our y value, meaning we cannot have an undefined value as the answer, we cannot have an indeterminate as the answer on y, nor we cannot have an imaginary number as an answer on the value of y. So upon checking this one is a constant function. Any number on x, any value of x, automatic, this will be our value of y. So we don't have a problem at all on that function. If you try to go over with the second function, we have x squared minus 3, that's quadratic in nature. If you try to check on every possible input of x within this interval, whether you will be obtaining a value of your f of x which is not undefined, not indeterminate, not imaginary, then that means we can conclude that our f of x there is continuous. So basically, once you have linear function, constant function, quadratic function, most likely we don't have an issue with that one. And if you try to look at also the domain of this particular function, we do have a continuous value of your x, so that means to say that. And also checking also your function there, we don't have an issue there in on the result of y, automatic that becomes continuous. So we've got continuous at an interval which is 2, 4. Let us now have another interval here. We have a half closed interval. We have open on 2 and close on 4. So if you are going to try to look at the how we look at the interval here, we have 2, 3, 4. Our 2 is not included, but our 4 is. And also part of the numbers that are found in between, those are also included. Now, how to deal with this, because this is not open. If you've got an open there, automatic, we can just simply look for numbers that will make it a break, a gap, or a jump within that particular function, and that will become discontinuous. But here we don't have an open interval, so which means that we need to satisfy conditions under this one. If that is half closed interval, we will be satisfying 2 here. First condition is that we need to satisfy the first condition that we need to satisfy is we are to check if f is continuous on the interval AB. Our A here, take note this is open interval. Our A here is actually this 2 here, and our B is the 4. Now checking on that one, the open interval, our AB there is, the function there is continuous because we do not include the number 2 in there. So again, testing out whether f is continuous on the open interval AB, we may try to get values in between 2 to 4 and try to plug it in here for, let's say for example, for 2.1. 2.1 is greater than 2, so that means to say we're focusing on this function here for every values between 2 to 4. So literally we're getting a value there. We don't have a problem there. We don't have a hole, we don't have a break, we don't have a gap. So that means to say that that is continuous on our open interval AB. So next, after the one, because this is half closed, you are going to go for the second condition. Second condition there is that we are going to check on this closed interval here, this number, which is 4, whether the function is continuous on that particular number. So if you recall, in checking for continuity at a number, we are checking for the 3 conditions, whether we've met that one. We have 3 conditions. One is that the f of c exists, and then the second one is that the limit exists, and then the third one is that they are equal. So we can simply summarize that one into having it as the limit of f of x as your x approaches. This time we're approaching that one on b because we have this as our closed interval. So we are going to check whether the function is continuous at this particular number. Now the values there that we are checking, since 4, if you notice on the number line, this is 4, the values once we approach our number 4 is gonna be coming from the left side only because our interval says so. We have 2 to 4. We don't have to check beyond that one. So our b there is gonna be, or our limit that we are looking for is gonna be, as x approaches, b coming from the left side. So this is now equal to the limit of, we are to check on what function we're using because this is piecewise function. And notice that the domain of this one here and the number 4 there satisfies the second condition. Your 4 there is greater than 2, so we'll be utilizing x squared minus 3 as a function as your x approaches. B there is the 4 from the left side. So since this is quadratic, that means to say we don't have a problem at all. We are going to simply plug in the value of 4. So we have 4 squared minus 3. This is equal to 4 squared is 16 minus 3. This is equal to 16 minus 3. That's equal to 13. We have that one as our limit of f of x as your x approaches b coming from the left side. Now let's go over and check, because according to the condition there on b, that your limit of f of x as x approaches b coming from the left side must be equal to our f of b. So we'll be looking for our f of b here. f of b would mean that we have that as f of 4. Now, since we're going to look for f of 4, we are going to look at the domain. Number 4 is also found in here. So we have that one as x squared minus 3. If we're looking for our f of 4, that means we are replacing x by 4, squaring that 1 minus 3. This is now equal to 16 minus 3, which is equal to 13. So again, going back to the condition, if you are going to look at our limit of f of x as x approaches to b coming from the left side, the answer to that limit is 13. F of b or f of 4 is also 13. They are equal, so that means to say that our f there of x is continuous at the interval 2, 4. So let's go over with the next one. So we are checking whether our piecewise function is continuous at the interval close interval 2 and open interval 4. So this is also a half closed interval. So again, since this is a half closed, we are going to check on the first condition that whether f is continuous on the open interval 2, 4. So upon checking that one, notice that on the interval 2, 4, so again we're going to draw our number line 2, 3, and 4. This is open. This is closed. This is open on that particular interval. But if you try to look at this, we are trying to look if, or to check if it is continuous at the open interval 2, which means to say that this is open and the 4 is also open. So since 2 is open, that means to say we are not having a problem here, because if you try to look at the values, you would really have no problem at all once you try to plug in those values that are in between 2 and 4. So our first condition is met. Our b here, we are going to check whether our limit of f of x as your x approaches a coming from the right side, ya coming from the right side. This is a, this is b. Our closed interval is on a. Our a is 2. This is our 2. Values of the interval are coming from the right side, moving closer to 2. So it approaches to coming from the right side. Will this be equal to f of a? So we're gonna check that one. So let's try first our limit of f of x as your x approaches a coming from the right side. We have limit of our f of x that we're using here is because we have there coming from the right side, the values on the right side of 2 are 3 and 4. So this satisfies this condition here, the second function. We have that as x squared minus 3 as your x approaches 2 coming from the right side. This is now equal to, we're going to plug in, we have 2 squared minus 3, this is equal to 4 minus 3. This is equal to a1. Next, we are going to check our f of a so that we can compare that one with the limit. Our f of a is equal to f of 2. Our f of 2 is equal to, our 2 there, the value 2, is found in here. We have that one as 1. Again, our value 2 is located in here. We have that as equal to 2, which means the 2 there satisfies this domain, and that satisfies the first function. So f of 2 is 1. So upon checking that one, if you are going to compare and check whether limit of f of x as x approaches a coming from the right side is going to be equal to our f of a. Limit of f of x as x approaches a coming from the right side is 1. F of a is 1. They are equal. So that means to say that we can now write the conclusion that f is continuous at 2, 4 interval. So let us now go for this one with a closed interval at 2, 4. So since this is closed interval, which means that we need to satisfy the three conditions. First one is f is continuous on the open interval AB. So upon checking that one, we don't have a problem with our open interval AB there, or open interval 2, 4, because once you try to substitute the values in between 2 and 4, we don't have really a problem with those functions. So this is a check. Let's go for the second one. We need to prove that our limit of f of x as x approaches a, our a is this one, our b is that one. Notice that on the number line we've got 2, 3, 4. Those are closed. And if you wanted to approach your a, which is 2 there, your values are coming from the right side. So that means this is a plus, which is going to be equal to an f of a. We need to prove that one. So we first get the limit of f of x as your x approaches 2 coming from the right side. This is going to be equal to our f of x with as x approaches 2 coming from the right side is on this second function, because approaching 2 coming from the right side, we've got the numbers 3, 4, which are greater than the number 2. So we'll be utilizing the limit of x squared minus 3 as your x approaches 2 coming from the right side. Since that is quadratic, we have to plug in. We have 2 squared minus 3. This is equal to 4 minus 3, which is equal to a 1. We need to check our f of a. Our f of a, or f of 2, we are going to get that one from our first function because we have that with equal to 2. So f of 2 here will be equal to a 1. Now comparing that one, we have a 1 here on the limit of f of x and a 1 on f of a. They are equal, so that means to say that this one is okay. We have now proven our b condition. Let's go to c. We are going to prove that our limit of f of x as your x approaches b coming from, b here is 4 coming from the left side, is gonna be equal to our f of b. So finding our limit of f of x as your x approaches, our b is 4 coming from the left side. This is equal to, coming from the left side, we have 3, 2 as the values of x, and the domain there is gonna be on the first function because we have that as x less than 2. The pointer is pointing to the right side, left side of 2, which means we are taking, we are considering, sorry on that one. We're not considering 1 here because our left side of the number 4 here are the numbers 3, 2. So meaning we are still on the second function. So we have limit of x squared minus 3 as your x approaches 4 coming from the left side. This is equal to 4 squared minus 3, which is equal to 16 minus 3, which is equal to 13. That's our limit. And then we need to prove that that is equal with our f of b. Our f of b, we have that as f of 4. F of 4 is going to be equal to, we are to look at where 4 is on the domain. 4 is greater than 2, so that means to say that we're considering x squared minus 3. So replacing x with 4, this is now 16 minus 3. This is equal to 13. So we have this one and that one as equal. This is satisfied. So therefore, we will now be creating our conclusion that f of x is continuous at 2-4 interval. So once again, this is your teacher Jenny saying good luck on every challenges. Practice and practice, and it will make you perfect.